not solvable for it. Except if Q is less than I think it should be n plus 2 to n. I think it's even
Okay, ladies and gentlemen, siesta is over. Time to work. I have a great pleasure to announce the talk by Reika Koizumi, and she will speak about temperature effect in the BEC model. Please.
Thank you very much. Thank you for the introduction. And I thank all of the organizers for inviting me to this nice conference. But I'm very, very sorry. So you see my title, temperature effect in the BEC model. BEC means Bose-Einstein condensation. It's the model of nonlinear Schrodinger equations, not related to nonlinear diffusion. Okay. And so it's very far from the topics of the conference. But don't worry. In fact, temperature effects gives in the nonlinear Schrodinger equations the dissipation effect. So that becomes finally the heat equation, the parabolic equation, Gibbs-Boulogne equation finally. So you can see. Okay, so this is a joint work with Anne and Dubois from École Polytechnique and Arnaud Dubuche from UNS. UNS Ukraine. So first, I want to briefly explain what is Bose-Einstein condensation. So this is from the Wikipedia, and this is simple explanation that a state of matter of a direct bosons particular, which are bosons, cooled to very low temperature and very low pressure too. A large amount to boson occupy the lowest quantum state, the least energy quantum state, where we can see macroscopic quantum phenomena. And this is predicted very old time by Bose and Weinstein in 1924-25. And in the physics laboratory, this is realized by the experiments. In 1995, there is very old topics now. But finally, since the realization was succeeded in 1995 by two American groups, and they won finally, I think 2001, something like that, the Nobel Prize for this experiment. And this is related to the experiment. The setting is related to the model equation, because we wanted to know the wave equation, the behavior of wave equation, wave function described by boson. The condensation of bosons. So first, I explain simply the experimental tools. So first, we need to realize very low temperature. So we use we just confine in this light box, and we use the laser cooling. First, laser cooling, and the particles will concentrate on the center of this box. But it's not sufficient, the laser cooling, so we need to the trapping potential here, like x square, typically x square potential, and we the particles, so the particle with high energy particle will get off this trapping potential if we decrease the height of potential. And finally, we can have just really the particle which has very low energy state here. So the modeling. So we consider the large amount of bosons, the x1 and xn, xn particles, the position of particles in the trapping potential, like this one, we call V potential. And we consider only two body interaction because this is in the low temperature state and low pressure state, and we can neglect actually the interaction, the big interaction between the particles. So we need only consider the relation of two particles. But two particles also, there are rarely almost no interactions. So we can put here in the Hamiltonian. Here, this is the kinetic energy part, and this is potential part, trapping potential, and this is interaction part between particles. And we can put as U as potential delta interaction because there's almost no interaction under the low temperature. And also we assume the mean field approximation we call Hartley approximation. It's just we can decompose the wave function. So this is the whole Bose-Einstein condensation wave function, but this is decomposed by each wave function of each particle. So it is a function. And by the scaling of large number of particle scaling, we have, but formally, we have Gross-Pitet equation. This is Gross-Pitet equation we call in this context of Bose-Einstein condensation, but this is only Schrödinger equation. So you can neglect the Planck constant here. Derivative in time psi equal minus Laplacian plus potential V of x for trapping potential plus the interaction of particle becomes just cubic nonlinearity. And we call this model typically with V of x equal x squared, we call Gross-Pitet equation. And I didn't say anything about the temperature here because we consider always that to derive this equation, that completely the temperature is absolute zero. The situation is absolute zero situation to derive formally in physics to derive this equation. But recently in the experiments, we understand that we cannot neglect really the temperature. So a little bit positive temperature we should consider if we wanted to analyze the behavior of wave condensation function. So in that situation, physicists proposed the stochastic projected GP. That means that stochastic term we add as a temperature effect, and in the same time with the balance, with a good balance, we add this patient here, this is Schrödinger part with I, and here, this patient part, it's just Laplacian here, without I. Laplacian part, the coefficient is gamma here, and W is space-time white noise. and space-time white noise in the correlation, in the delta correlation in time and x, and the coefficient is here, gamma. And with this balance, keeping this balance, we should, so physics propose group theoretic equation like this, with temperature effect, keeping this balance of coefficient in front of dissipation and space-time white noise. Okay, so my motivation is to analyze this model proposed by physicists to describe the temperature effects in the process and condensation. And first, if you consider the deterministic Schrödinger equation, nonlinear Schrödinger equation, normally we are interested in the stationary state, like standing wave solution or something like that, the stationary state, and if the stationary state is stable or not. Because if we find a stable stationary state, these states will describe the long-term behavior maybe. So if we consider the deterministic Schrödinger equation, we know that there is a global minimum of energy, and this should be stationary state and ground state solution, and that's stable. That let t equals 0, I mean that this is the temperature. Temperature is completely 0, absolute 0. We have the ground state. By the way, if we add the temperature is positive. In such a case, the way of looking at the model is completely different because this is a stochastic model. So this is a kind of, if we want to stationary states, that means that the equilibrium, statistical equilibrium states. That means we want to see the Gibbs equilibrium, Gibbs measure. The Gibbs measure is this is the energy for the deterministic equation. This is energy for Hamiltonian for deterministic equation, and exponential. So the form of Gibbs measure is exponential to the power of minus this energy. And d psi. So d psi is wave function for the model, but this means nothing. This is not rigorous, of course. So we want to give a sense, make sense. This measure, Gibbs measure, first in mathematics. Also, we wanted to analyze. So maybe physicists proposed this model, but we don't know if there is existence solution or justification of model, local existence in time or global existence time, and global solution. If we have once global solution, that global solution will approach it to which state, but we can expect that if there is a Gibbs measure as a statistical equivalent state, we can expect that the law, this is the stochastic version, so law of wave function converted to Gibbs measure as t goes to infinity. So we wanted to show that phenomenon in mathematics rigorously. Okay, so this is dimensionless form. So we forget physics now. So from now we do mathematics. So simply, I think we want to consider this stochastic partial differential equation, deep C, I plus complex unit I for the Schrödinger, and plus gamma is dissipation. Gamma is dissipation, and Vx is x square, I assume, and plus square root of 2 gamma dw. W is space-time white noise, but in mathematics, we say that W is a cylindrical Wiener process, M2, and we described in this infinite series of all the dimensions, infinite dimension, spanned by the eigenfunctions. HK, in this case, HK is eigenfunction for the linear part of operator, namely minus Laplacian plus x squared, because wherever x is x squared, the linear part generates the eigenfunctions. This operator always have only discrete spectrum, and lambda k square I denote corresponding eigenvalue. And so definition of winner process is like that. So W is the infinite sum of Brownian motion beta k. Beta kt is Brownian motion, and Brownian motion runs all over infinity the direction like this. And this white noise setting is derivative formally. So Brownian motion is not differentiable. But formally, if you consider the derivative of W, we can put this here as white noise. Okay, so we wanted to see the local equidistance, global equidistance solution of this stochastic PDE. Also, we wanted to construct the statistical equilibrium Gibbs measure. And Gibbs measure, there are many researches in the world. So first, Simon Leap started to look at the statistical state as a context in the context of constructive quantum field theory. And next step arrived in the field of nonlinear dispersive equation as Hamiltonian system. As Hamiltonian systems, for example, Lubovitch, Rhodes-Spear, Bourgain used Gibbs measure, so constructed Gibbs measure as invariant measure for the Hamiltonian system, and they used this invariant measure to globalize the local time in time solution. The typical Hamiltonian system, we can see the dispersive equations almost all Hamiltonian systems. So since then, a lot of researches exist, like by Nicolas Buch, Patrick Gea, Laurent Thomas, Nikolai Beskov, Coriander, or Bourgain, etc. And this is for the deterministic nonlinear dispersive equations. And now we move to stochastic field, because recently the physicists proposed a BC model with temperature effect. And in fact, already there are some results about the Gibbs measure, and Caroline progressive Lubovitch, and us, Dubas, and me. And also, on the other hand, there is a trend in the stochastic PDE's fields because there was a breakthrough result by Martin Heiler, 2014. And they analyzed a little bit different model, but this is a heat equation, just a heat equation, but space-time white noise model by doublet distribution, Heiler, Weber, Albedo, Kusuka, Grubinelli, Hufmanova. All things really now it's very hot topic and domain in the field of stochastic PDE. So we wanted to justify the Gibbs measure, but in the infinite dimensional case. So we consider first simply we consider the case spatial dimension D or 1, and how we can construct the Gibbs measure. And we consider Hamiltonian this one, and A is in one dimensional case our linear operator, harmonic oscillator minus Laplacian plus x squared. And we may formally write so that this is a formal expression of Gibbs measure exponential to the power minus Hamiltonian deep side, but there's no sense here. So we write this expression, the nonlinear part in the function of h psi, and the linear part exponential minus 1/2 the linear part how to say the functional deep side. That in fact, if we project on the finite dimensional case, so writing the decomposition with the orthonormal basis HK eigenfunctions, and if we look at just until n mode of eigenfunction, we can give a sense to this linear part of functional deep slide, because this is really the form of Gaussian measure in finite dimensional Gaussian measure. And but to construct, so to give a sense law, so give the measure, we are interested in the give the measure, that means that we have to add the nonlinear part in the functional. So how to do? So we cut off again the psi, by function psi until n go large n, and we consider which topology this stuff can converge. It depends on really the topology. If we want to justify the existence of given measure for our equation for circuit PDs. Actually, the support, so I mean that the support of given measure where we can find, that's the problem always. The first question for the circuit PD. And in fact, it is known that if you consider to know the support of Gibbs measure, if you consider the stationary solution of linear part of equation, so linear stochastic equation, this stationary solution has, in fact, the same law as Gaussian measure. We can see not trivial, but it is rarely known in the probability theory. So just to know, in order to know where is the support of Gibbs measure, the Gaussian measure, it is sufficient to know that the stationary solution of a stochastic linear equation, in which space that lives. In fact, we wanted to know first. And this is, in fact, calculated using the decay property of eigenfunctions and also eigenvalues in terms of k, because this is, in fact, the infinite series of something described by eigenfunction and eigenvalues. So since now we know that the decay property, the assumptive behavior in terms of k, here lambda k square is 2k plus d, these dimensions. So we can use this order in k to calculate infinite series here. And in one-dimensional case, in fact, we know, so we can calculate that this stationary solution lives in LP. P is larger than 2. Thanks to the information from the eigenfunctions, eigenfunction decay of eigenfunction. This is proved cohort. So now we are interested in constructing the local in-time solution on the support of given measure. So the first one-dimensional case, I showed you that the support of given measure is in LP, any LP for any P is larger than 2. So we assume that P is larger than 3, and we can construct a solution in LP. But almost for almost all with respect to Gibbs measure, or for almost all initial data with respect to Gibbs measure. And also we can answer the question that assumptive behavior. For example, the wave function, the law of wave function converged to this statistical equilibrium Gibbs measure or not. Yes, we can prove that this convergence as assumptive behavior. Also, the rate of convergence to this statistical equilibrium is, we can say that explicitly exponential minus gamma t. Gamma is the dissipation coefficient in the equation. this is one-dimensional case, and it's not so difficult, I see. I want to say. And I go to dimensional 2. Dimensional 2, the situation will change completely because, so I told you that to know the support of given measure, we have to know that the regularity of stationary solution of stochastic linear stochastic equation Z. And dimensional 2, with the same kind of calculus here, we know that Z is in W sobre space, W minus SQ. S is any positive. So that means that we cannot have Z as a function, the distribution. So minus with negative regularity, always negative regularity. So it is difficult to so if you have the distribution with negative regularity, we cannot define the multiplication, for example. To define the nonlinear part, we have to define the cubic multiplication. But negative regularity distribution, cubic multiplication cannot define. So now this is a technique we call double distribution trick. We decompose U plus Z. Z is bad part, Z is negative negative part, and plus U. And U satisfies the random PDE. So psi is a solution, assuming that psi is the solution of this two-dimensional gross-plate equation with temperature effect. And if we decompose bad part Z plus U, actually we expect that U is regular part. And U satisfies this following random PDE. And in this random PDE, there is no stochastic thing. Stochastic thing. Just there is a random element as Z here. So we can use the deterministic PD technique to analyze this PDE, this equation satisfied by U here. But the problem is always from this negative regularity of Z. For example, here, Z cubic here, Z cubic here, and Z square here. We cannot define this term, actually. So we denormalize the bad part from nonlinearity. The technique is we call always weak denormalization. We use the weak product defined by Emisión functions, and that works. In fact, that well works. We know that from the probability theory, and we extract the bad part from nonlinear part, and this stuff is replaced by always this stuff, and we succeed. In fact, local equidistance of solution, but in the sense that we extract the bad part. So I mean that there are some assumptions for the space, regularity, and integrability, but it's not important. Just if you consider this decomposition, double trick, psi equal U plus Z. Z is this space. And if you extract psi from psi, Z element, we can have a local equidistance of this solution U satisfied this PDE, random PDE. So this described this in this theorem here. And U is in W minus SQ, in the same regularity of Z. And also, if we just LR space in time, W beta P, beta is positive. This is a very standard deterministic PD statement. This is done using the heat semigroup property here. And also, not for the nonlinear terms, we use this type of bilinear estimate. And also, we can prove that global equidistance, so globalization of local solution using the energy estimate. The norm is LQ norm. But to use this energy estimate, a little bit technical thing arrived. It's not directly used, but we use a little bit a kind of bootstrap argument. Since this is linear, this is heat, semigroup is typically heat semigroup, we treat. So if the time is time passed a little bit, we can gain the regularity. So we repeat, we gain the regularity, and finally we can globalize. We can gain until the regularity which covers this energy estimate, and we can use finally this energy estimate, and we can globalize the solution. This is the idea. So my time is
No, still 10 minutes. Stop me. Go.
okay.
We enjoy. Please go ahead.
Okay, this is the idea of bootstrap argument, but I add something again. So in 2D case, we succeeded to construct a local in-time solution here with a completely deterministic argument. But to prove the equidistance of construction, to construct the Gibbs measure, it's different too. And if again I write the Gibbs measure, the nonlinear part and linear part, here this is Gaussian always. This is the Gaussian part that doesn't change. But since the supporter of linear Gaussian part now equivalent to, so we know that equivalent to the regularity of Z, which is negative regularity. So we cannot define here L4 norm. The psi. So psi it should be in the support of Gaussian measure, which is negative regularity. So we cannot define the L4 functional. So we need, so in the Gibbs measure, in the form of Gibbs measure, already we need to renormalize again the nonlinear part here. And we have to take limit. So I mean that I explained that to construct the Gibbs measure, first we cut off, we consider finite dimensional Gibbs measure, and the limit, if it exists, in which topology, I don't know, but if it exists, that we call the Gibbs measure for the infinite dimensional case. So this works if we again renormalize this nonlinear parts too in the formal description of Gibbs measure. This is the result of equidistance of Gibbs measure because we consider, so we cut off the functions like this, and also this is a little bit complicated version, but this means that we renormalize the nonlinear parts and finite dimensional version we consider, and the question now to prove the equidistance of Gibbs measure, the question now, this measure is convergent or not. And if it is convergent, the limit we call Gibbs measure in the two-dimensional case. And this can be done. So this is the result here I wrote. In fact, the weak limit we can establish other limits. And this limit is invariant measure for whole dynamics, whole stochastic PDEs. So we can use to globalize. So also we can use this invariant measure to globalize solution. And finally, so we construct in two-dimensional case with the use of renormalization procedure in the Gibbs measure. we succeeded to ensure the limit, the Gibbs measure for the circuit PDEs we treat now. And so what? So now what is the property of measure? The question. Because in two-dimensional case, this is rho is just a weak limit. So compactness method gives a limit, some kind of limit as a measure. But you see in for example, so this is the one-dimensional case. One-dimensional case, we don't use any renormalization procedure. Just directly this stuff cut it off on the finite dimensional case, convert directly, keeping this form of measure to Gibbs measure law, in fact, in one-dimensional case. So we know that already this Gibbs measure is absolutely continuous with respect to this Gaussian measure here. So one-dimensional case is nice property as invariant measure. But two-dimensional case is just we ensure a weak limit. So we don't know the property of this measure. And finally, we can answer as a property of measure is rho is absolutely continuous with respect to Gaussian measure or singular with respect to Gaussian measure given here from the linear part. The answer for two-dimensional case is, in fact, Gibbs measure and Gaussian measure are mutually singular. And this is proved by using the Balashukov-Brunelier, its recent paper to construct. So they used the method used variation formula by Bouet Dupuy to construct the 543 measure. Okay, so we are interested in fact, our motivation is physics from quantum physics. So we are interested in fact, not in one-dimensional case. The important case for physics is d is equal to 2 and d is equal to 3. And really hard because all things are roughness coming from the very irregularity from the space-time whiteness. Actually, white in space is really a problem too. So as the external force term in the equation, the white in space noise gives very bad regularity to the equation. We cannot easily justify that equation. So that irregularity of space white noise increases. So irregularity, the negative regularity of white noise increase if dimension increase. So the problem for d is equal to 3 is very difficult. So higher, much higher gains the field price. But okay, so this is continuous. So this work is continuing progress for two-dimensional case, three-dimensional case. But the idea is I listed on, but this is a very terminology for probabilist. So I skip this and I stop here.
Questions? I will begin my questions. I want to understand this difference between deterministic argument and probabilistic. You have this Bose-Einstein condensate model without white noise and with white noise. So when you have without, I can imagine a priori estimates, energy inequalities, and existence of solutions. But when you study this white noise, you use this D'Aprato trick. So you can make equation with random coefficients, but then more or less you proceed in the same way.
The same way, exactly. This deterministic PDs, in fact, finally. So the pathwise analysis governs.
So why? But I want to understand. So why cannot go to 3 dimensions? Because of problem of white noise.
Yes, because of white noise and the very so minus regularity. So in two-dimensional case, it is still W minus S. How to say? Well, here. So W minus S. S is any positive. So we can take very small s
Here. Okay.
very small s.
Okay.
And if you consider the multiplication z squared, z3, z4, anyway, it is very epsilon, negative epsilon. So we can expect that always negative epsilon. Yes, but in three-dimensional case, this cannot be the same situation because minus, for example, minus 1/2, minus 1.
Okay, but this Brownian motion, infinite dimensional, is it given by physics or this is just mathematical idea? Because there are different random motions which you can add to the equations, which are not so bad.
Okay, so there is a research. There is such research, many research, because it's easier to solve.
Yeah.
So that means that not necessarily for white,
Okay.
but colored in space,
Colored,
regular. We can consider easily, in fact, nowadays.
So that's easy, so it's not interesting. Now I understand. Okay, thank you. Thank you. You don't want to go this easy way. Thank you.
So, yeah, thank you for your interesting talk. Can you express for the global stability or TDK? Global existence.
For
Global existence.
Global existence.
global existence, for in which case?
In higher dimension,
Higher dimension. I don't know.
TDK.
Just
Yeah.
two-dimensional case, pathway analysis works.
Okay.
But three-dimensional case, by the way, if you don't know, if you don't have x squared term here, it is not global existence. But so the difficulty in our model is also from this decomposition is special because we use Emisión function as an eigenfunction of minus representatives x squared. So if you consider on the torus,
Okay.
torus is very easy, sorry, very easier because we know Fourier analysis. We can use them.
Questions? Okay, let us think later again. Thank you very much. 5 minutes of break. Relax. I think stability.
これがこれを送ると、これを一番最後に見るのかな。一番最後になると、この子の
マスターですか。
このストロングゼラと入れるやつが2つ揃うと、キャンプコンバージョンができる、そのステージな状態に行きますが、入れるんだけど、これがすごい。
I was trying to start with the customer. But it's
Can you open my slide?
You want to have this?
No. I have
Yes. Yeah, sure.
Where did you I guess that's your desktop. I would October's there.
Yes.
I didn't come to your call because
Good. Because
the morning would be difficult.
if you could come, you would solve for my problem. So I'm happy there's something left for me still.
But we can talk about so when did you put goodbye?
Yeah, before lunch.
With all peace.
Before lunch.
Before lunch today.
Yeah,
Please
yeah,
please take care.
So let's open.
No, not. Yeah.
But you put your slide by USB, right?
USB, yeah.
Stop it now. Millions, right?
No.
Eh?
Boom.
Boom. Do it. Yeah.
Oh, that's you. I know your papers. Look, I know your papers. Now I have a chance to meet you. I'm glad.
What is CAS?
CADD, the Chinese Academy of Science.
Okay. In Spain is cycling club.
Good. Welcome back. Next talk this afternoon by Hook Hong Yen, and he will speak about regularity theory for the Landau and non-cut-off Boltzmann equation.
Yeah,
Please,
yeah.
all is yours.
Yeah. Thank you very much. Thank you, Jean-Louis, for inviting me to come here to attend the conference. And today I will going to talk about for the regularity theory for the Landau and non-cut-off Boltzmann equation. And yeah, according to the kinetic equation, the name is kind of different than another talk. Yeah, but namely that is the non-local equation. Extremely non-local equation. Somehow it looks like porous medium with non-local pressure. If we consider for the homogeneous case, you will see it later. So what is the Landau and Boltzmann equation? That is the equation. We have the linear term. It is the transverse term, and equal the right hand side is the sonotone QSF. F here it is the divided by the density of the particle in the gas, and we will consider for the general domain. In S and V here, this is the velocity, and this is of course in OD, and with some Pauli condition, we will discuss about it later. And for QFF, here it is the sonotone operator. This is only the operator. This operator only react to the V variable velocity. Yeah. Velocity, and this is the quadratic integral operator. And for this equation, that is the so for QF here, I consider F between 0 and 1 or equal to 1, and with F between 0 and 1, we call it the Boltzmann equation. And then when at conversion to 1, we obtain the Landau equation. So for the equation, that is very important mathematical model of the statistical evolution for the last number of the particle interaction via sonotone, and this is introduced by Maxwell and Boltzmann. So what is the sonotone operator? So because it is bilinear, it is better. We will define that operator in terms of two functions, F1, F2. And the first I want to consider for the Landau case when S equal 1. And for when S equal 1, we can easy to see this is the divergence of the matrix A convolution with F2. The matrix A is the kernel, something like the kernel of the Greek equation, but but this is the matrix. Okay, sorry, this is the identity matrix and multiply Z here. So when gamma plus 2s is negative, then this one is the like risk kernel, risk operator. Yes. So and this is divergent of the and of course we consider FAT positive function. Then this matrix is the positive, and then this one is the like second order of with second order with respect to V variable of the function f1. And for the second term, it is lower term because we move V derivative to this function. Okay, so let me write down. So the kernel, when we put this one, it looks like V fractional of power A of F with a positive. Yeah, in the case, okay, with a positive. And then we can see this one is the second order of the with respect to V variable of the function f1 and with coefficient depend on f2. Yeah, and it is lower term. Yeah, because this one is the second order, and this is the only the 2 minus a derivative. Yeah, and then we can see here the main term of this operator is just only the second order, but for the coefficient depend on solution. Yeah, even this case is the local, but coefficient non-local, and this one it look like the post medium. Yeah, some kind of this. Yeah, and yeah, for the Boltzmann case, S between 0 and 1, that is quite complicated. Yeah, this is the operator defined by interaction between F star. Yeah, we define by this. Yeah. So and we take the integral in V star and in sigma on the square. So maybe we this is the notation in the kinetics, but the pupil from the classical BD, maybe we don't care about this because that is very complicated. I will simplify this operator in the next slide. So and for the operator for the kernel P is defined by this. Yeah, is defined by this. It is the B star minus B and a sigma B. We consider for the kernel like this. Yeah, and with P small b here, it behavior like this. And for the kernel Landau K, the kernel here, the Z of power gamma multiply Z of power 2 and multiply identity matrix and minus Z tensor with Z for some quantity C. And we can check mu is Gaussian. It is the equilibrium associated to Boltzmann and Landau equation, because we have the by this definition we can see yeah QF mu it is 0. Yeah, and then of course we can see this one is the solution of the transport equation, because for equilibrium it is the independent in time and independent in S. Yeah. Okay. So and then yeah, and then for the definition of the Soleton operator, we can write by this form. We can write by this form. For the Landau case, yeah, we can write by divergence of A convolution F2 multiplied with F and minus. Okay, this is lower term. Okay, we can put this one on the right hand side, and we just care about this term. Yeah. So and for the Boltzmann case, we can derive by in terms of the fractional operator of order. Okay, so of order 2s of order 2s and plus lower term, and this term is the f1, and this operator like the risk kernel in terms of f2. And what is the operator QS here is defined by given by this formula. And for the we can see that this is the operator we usually do consider this, and this coefficient here is the equivalent to 1. Yeah, we bet this one equivalent to 1, and this one is the fractional of order S here, minus Laplace, which is back to V variable of power S. Yeah. When coefficient here is published from below and in the pole, and for the coefficient here is defined by this. It is somehow some kind of a risk kernel, but we not take for the integral on the whole domain. No, on RD we just take the integral on the octonal in Z. Yeah, in Z. Yeah, in Z. Yeah, and this operator in some paper about Boltzmann, they call it the anisotropic operator. Yeah, an anisotropic operator. And by property of P, we can obtain capture A rho equivalent to 1. Yeah, and then this one we can drop this one. So and for the elliptic PD or parabolic PD, we usually use we usually use degenerate or non-degenerate. So and for physical problem, we call vacuum. This means the coefficient is degenerate at some point. Yeah, this means the coefficient C here can be equal 0 at some point. Yeah, this is the degenerate, and non-vacuum. This means the coefficient far from vacuum. This means far from 0, and this is non-degenerate. Yeah, it means the coefficient is chiefly positive. Yeah. So and so for Landau and Boltzmann equation, that is exactly coefficient linear degenerate fractional Kohlrausch equation. Kohlrausch equation associated to S equal 1, and fractional Kohlrausch associated to S less than 1. So this is the Landau equation. We prepare again, okay. So we don't care about this term. We just care about this one. This one is in order, and with the matrix, with the positive matrix depend on F. And okay, so for this operator and for the homogeneous case, this means the density independent in the polarization. This mean independent in F, and then we will obtain the symbol equation without transport term, and this one is the equation. It look like Borosmir with non-local pressure in some sense. Yeah. And for the Boltzmann case, this is the fractional. Yeah, this is fractional, and we have the term. We have the extra term. This is F, and multiply F convolution with this kernel. And note that this coefficient here, somehow, when we take average in the whole direction with theta here on the square, and then we can easily to check this one equivalent to the F convolution with this kernel. And this is the risk operator, and then we can see this one is the related to the in the class of weight A1. Yeah, Morgenhaus weight A1. Yeah, because for the last BD, there are several ways they consider coefficient depend belong to this class, and then we have the several results about relativity. And for the homogeneous case, we have this equation. Yeah, we have this equation. Yeah. So if we consider for Landau and Boltzmann equation in terms of this whole formula, this one is the similar to the top bit in this conference. Yeah. Okay. So and what is the scaling property of the equation? We can check with F. F here is the solution of the Boltzmann-Landau equation, and then and then F lambda here is defined by this for any mu in R and lambda positive. F lambda still solution of the equation. Then because we will go into to study Landau and Boltzmann equation using the smooth effect associated to the this term associated to the fractional Kolarov equation. Yeah, associated to this one. And then we can look at the first term and second term. It is the fractional fractional heat equation associated to V here. And then it is natural, we take the mu here equal 1 over 2f. Okay, it is consistent with the scaling of the fractional heat equation of order 2f here. Yes. So and then when we fit the parameter mu, then we can obtain the family norm of solution associated to Boltzmann equation. We have the norm F here in LP1 in time, LP2 in V, LP1, LB2 in S, and with the P1, B2, B3 satisfy this condition. Yeah, this equation. Then this norm is the critical norm. Yeah. This means this is the scaling value associated to the problem. Yeah. And we also have another norm in the case B1 equal infinity, and it is the best subspace. Yeah. It is the best subspace. Yeah. So what is the relative result? So we have the several results about Boltzmann and about first we have the few results about homogeneous Boltzmann equation, and we have a result a solution becomes smooth in the K gamma plus 2F positive and wrote by several wrote by depressed and hit correlator and the root from Japan and in China. Yeah. So this is only the homogeneous. This is only the homogeneous. It is EGK to do. Yeah. And more if initial data very close to equilibrium Gaussian, yeah, then we can drop the equation. We can drop there is global smooth solution, and this is dropped by Boltzmann and the person, yeah, and more we also have the result for the criteria if we can prove solution of the inhomogeneous Boltzmann equation. It is smooth when we assume F here is too rare enough and F here far from the vacuum. Yeah, the coefficient should be positive. Yeah. Then we can prove that. So and it is very recently the important work by the pupil come from classical BD, Sylvester. Yeah, this is the guy. He the expert in the fractional, and he know quite well about the deoxy, and he bring the classical tune the deoxy tune to the kinetic equation for he study using the Yoxi method to look solution of the Postman facility C alpha, C alpha, and after that using the bootstrap argument using the shoulder estimate to obtain solution is smooth, but he needs the assumption. He needs the total mass, the interval in velocity, it is the power is from below and above. And for the N to B, it is finite, and N to B and energy is finite. And in this case, we only heat is only available for gamma plus 2s between 0 and 2. And he can drop solution is smooth. And also the result is 10 to the Landau K. It is a very important result in the kinetic theory. So, and let me check the condition of the of their condition. So we take we replay f by f lambda, and we take subminimum in time and in s, and then by changing variable we can obtain this sub equal this sub and power lambda. And multiply lambda power gamma plus 2s over 2s here, and then we can see this norm it will be subcritical when gamma plus 2s chiefly positive, and gamma plus 2s negative, that is the supercritical, and critical case this means gamma plus 2s equal 0, and because he assumed this condition, this is the f multiply logarithm of f, it is finite, and somehow it is the slightly subcritical. For the k gamma plus 2s, it is positive, or equal 0. So now up to now, there are no result for critical spaces. Even for the simple model. So and what is the tool to study relativity of the equation? So we can use the standard method, it is the energy method. In the Sobolev space in L2 setting, we multiply that function, and we will use causality estimate for solution operator, and moreover we to get smooth effect substitute as variable, we need to use the average lemma. That is the deep result. For average lemma for the free transport operator, because for the transport operator, when we multiply that function, f is that function, or the function phi in terms of f, and then we take integral in s, integral in v, and then we get nothing. We get 0. We will not get any relativity from this part, but we have the way to do that. I will explain this later. So and second method, developed by Sylvester and his co-author and him best. They use the maximum principal given to get the LNPT bound, and after that, from LNPT bound, they use the Yoxi method to get the C alpha, like coefficient in about this from below and above. Then he can drop the C Holder relative. And after that, from Holder relative, then he obtained the C infinity using shoulder argument. So, and this is my result. This is the result. We can see for the boundary set here. So, and we can see the problem, the Boltzmann equation on the whole domain. On whole domain, and with the index gamma greater than minus d minus 2s, and with the initial data, it is positive and smooth enough. And then we can do if F here belong to critical space, yeah, critical space, and with P1, B2, B3 certify this, and this one is the certified critical space if gamma fluctuates less than or equal to 1. Yeah. And for this condition, we need to have the some decay at infinity of the function f. And then we assume the coefficient strictly positive. We assume the problem is the non-degenerate. And then for the endpoint k, this means b1 equal infinity. Then we need an extra assumption. Yeah, we need this norm, and in the set of lambda greater than f greater than lambda, and this is too small enough when lambda conversion to infinity. Of course, with f here is decay enough and at infinity, and of course this limit is equal 0. Yeah. So and then in this case, we can drop f here is smooth. Yeah, smooth. Yeah, C infinity. Yeah. So this is the first result for the Ladikh-Keza-Plaut criteria type for the Landau and Boltzmann equation. Yeah. So yeah, for the Nemthorpe equation, there are several results about this criteria. Yeah. And so LB, LQ. Yeah. And so how we can obtain the D condition. So if we assume the initial data, yeah, positive, yeah, F0 SV greater than 1 over brackets of SV power n. Yeah, this means this is brackets Vs here. We have power n is divided by square root of 1 of s square of b square here, and power n. Yeah. So and we assume initial data boundaries some quantity c of Vs n. Yeah, for some n. Yeah, for some n. But of course we can take n greater than 2D, and then greater than 2D, and then our initial data is the finite total mass. Yeah, yeah. This can be initial data, can be integral L1 in F and in V. Yes. And after that, with this condition, with the strictly positive, and then we can drop the limit indeterminateness of solution still hold. Yeah, and then using this estimates, we can obtain this one, and then we can remove this condition if we assume initial data like this. So and then for the so this is the case we can do. Yeah. So and when the case we consider for the coefficient, this condition is strictly positive, yeah, strictly greater than V of power 2s gamma. And then we can check the operator minus QS FF can be presented by something like fractional operator. In we can divide two components. Yeah, we pick E direction E, and this is the fractional only the direction E here. This is fractional. It is defined by this. But we take the Fourier, and then we obtain this is C multiplied E of power 2s. Okay, and then when we apply this operator to F, and after that we take E equal this direction V over absolute value of V. Yeah, and plus the operator associated orthogonal with E. Yeah, with E. This is this operator in the in the orthogonal with E here, E defined by C square minus C square minus C power E power 2, and we take the power F here, yeah, F, and we have the different, yeah, power. We have the different way, this way and this way, yeah, in this direction we multiply V of power gamma, and in another direction we multiply V, the bracket of V of power gamma plus 2s. This is the Chern-Ripple bracket is defined by this way: square root of 1 plus V squared. Yeah. So and then when we consider this operator when velocity is bounded, and then of course this one equivalent to the Laplace fractional minus Laplace of power minus Laplace of power s power v, because this one when we bound this one equivalent to this one, equivalent to 1. Yeah. So and then and moreover, if we assume initially right bounded some way Vn the F0 SB multiply the bracket of V power capital N, and it bounded, then we can drop this one. We can obtain the HMS, the higher radiativity, and somehow this is smooth effect. Yeah. And so now okay, so for Boltzmann equation, how we can get the radiativity in terms of S variable? Because for the Chern-Ripple equation, we can see if we multiply the test function either f or the function phi in terms of f, then when we make the integral in v and in s and in v, we get nothing. We obtain we can put this guy to here, and then we make the integral by part, then we get 0. So how we can get the result? It is to get the radiativity in S, we can consider for this test function. The test function is we multiply the test function is G derivative in Vj, derivative in Sj. Yeah. And then we can use integral by parts. Then we can obtain minus of 1/2 of the integral of the one derivative of Sj of G. Yeah. And this is the way we get the radiativity in S. Yeah. So and how about the equation on the body domain? We consider the domain with CS less than 1, and it is connected about the domain, and we see smooth function it like distant, and we assume derivative of C here. Of course, we assume derivative C here different 0 at the boundary. At the boundary case, this means the CS equal 0, and we define by standard notation that the Sn is our normal vector. We define by this. Yeah. And we define the phase boundary about omega E gamma the boundary omega times V or D. Yeah. And we decompose phase boundary to parts. Yeah. This is with the n multiply V less than it is the incoming boundary, and it is positive. It is outcoming boundary, and when this one equals 0, this is the singular boundary. Yeah, and for the Boltzmann equation on the domain, and yeah, the singular point only belong to this set. So, and we will have the four general physical kinetic boundary conditions. First, in the flow, we only need F here. Yeah, reach to the gamma minus equal G. G here is data. Yeah, G here is data. And the second boundary is the bounce part. It is the when we reach the F in the gamma minus, then it is equal F minus V here. Yeah. And second one it is the specular refraction. It is when we reach this one, it is gamma minus, and then this is equal F in the this operator. It is like yeah. And the last one is the non-local, very non-local boundary condition. Yeah, but very non-local boundary condition. With the condition, we can refer the existence of this equation. So and There are very few results about for the Landau and Boltzmann equation on the body domain. This is saw a few results in the group of Yangu and his co-author. Yeah, and they only look for the Lipschitz priority in V and infinity in S in time, and Honda in S and in V. And Sylvester and Chu, they study kinetic Fokker-Plonk equation for the four conditions. Three conditions: in flow, specular reflection, and diffusion reflection. They look for solutionality Honda priority, and recently they attend for the kinetic Fokker-Plonk equation to the non-cut up Boltzmann. Yeah, only the K gamma plus 2F between 0 and 2, and they consider for Pauli condition. They only look for solutionality infinity. Yeah. So, and this is how I attend my result on the whole domain to the boundary domain. We assume the same condition like we did. I mentioned before for the equation on the whole domain, and then for the solutionality, we will smooth the interior, yeah, inside of omega, inside of omega. This means we will smooth outside the set gamma 0. This is the singular set, yeah. And if this set is different 0, yeah, this is not empty, yeah. So, and solutionality may not smooth in gamma 0. Okay. So for the first condition, it is a specular reflection. We can draw solution F C infinity up to the boundary, yeah, up to gamma 0. And for the inflow, we only look F minus G. F minus G. It is C alpha in V and in S C alpha over 2S plus 1. And we have the similarity for diffusion reflection. And then for last condition, we only obtain the infinity. We don't know how to do. We don't know how to get this Honda rarity. Yeah. So and here we have some remark. We can obtain the result. We can somehow obtain solution in terms of this part. This is from C alpha plus 1, C alpha plus 2, yeah, something like this. Yeah, we can construct an additive operator in terms of F. Satisfy this one is the in the C alpha 0 plus K, yeah, and we have this one. Yeah, we can construct implicit this operator. So and moreover, the Honda rarity in the flow boundary, we can prove the optimal. For the optimal rarity for another condition, we don't know. Yeah, and why spectral reflection we can obtain the solution is smooth because we have the one way to reflection of solution on the whole domain. When we reflecting boundary condition, we will obtain this. And then after that, we will using this extension, then we can obtain solution on whole domain. And after that, we can study equation on the whole domain, and we obtain the solution is smooth. Yeah, but for this extension, we cannot obtain. We cannot apply this changing variable, this extension for the another boundary condition. So we have some. Okay, so now let me discuss how we can 2 minutes. Okay, thank you. So for this slide, I discussed how we can compute the exponent, the exponent alpha 0. So by standard argument, we if we want to study relative onboarded domain, we need to study the equation on the half space. And after that, we change in variable. We take the Fourier, and after that, we will obtain the equation with the two variable in Z and in W. Yeah, Z associated to S and V associated to V. Yeah, and after that, we can easily to obtain the kernel of this operator, and then we obtain this one. We can obtain this one. So and then the main problem we need to solve this one. We need to solve G in terms of data. Okay, to do this, we need to take the Z conversion to 0. And when we take the Z conversion to 0, we get this one. Not that this function, this is the view jump when Z equal 0. When Z equal 0, we take this one, Z equal 0, but we plus this one. It is this container. And moreover, this operator it is smooth for H W. And then we need to study this the integral equation. Yeah, it is the 2S plus here and this is the solution with this operator. Or here it is smooth, but we need to find the function S. So to do this, we can drop the unit alpha satisfied when we take the SW equal this power. We can drop this one. We can take this. We can replace S here by the polynomial function W power alpha here, and then we take the derivative here. Then we can drop this one. Behavior like can power by W of power alpha when V conversion to 0. And using this computation, we can obtain the formula of this solution. We satisfy this one, and then we can drop W here is unit, and we obtain smooth, and it is global. Yeah. So and we have the sum open problem. Maybe the second equation, that is the second question, it is interesting. Like we study for the natural equation because we don't know whether the solution is smooth or not, and we should estimate the how big for the single set of the solution. So we will expect the single set of the Boltzmann equation with respect to this house stuff with this matrix. And another question is whether we can construct global scaling variant solution associated to this data. And the last one is the whether we can convert for Boltzmann equation near to mass variant. This is the main important problem. And not that for the nonlinear Landau damping for the Boltzmann on T. That is the main open problem in the kinetic theory. And for 12 years ago, Silis Vinani, they solved this problem only on the periodic. So on the periodic, if we consider on whole domain and or stability, and that is less more similar than on whole domain. Yeah. So I stop here. Thank you.
Thank you very much. Please.
You had a condition of the type of Serrin-Ladzinskaya for the regularity solution, right?
Yeah.
But you don't find these kind of conditions in fractional replacement flow. This looks like a Navier-Stokes.
Yeah, it looked like Navier-Stokes. Yeah, this is the first result I only consider for the case in the LBLQ. Yes.
Navier-Stokes with fractional Laplacian.
Yeah.
Yes.
Yes, my question is, if you can go to the first slide, please, I would really appreciate. Is this one. And if you have some integrability with the right-hand side,
yeah,
can you transmit this to the time derivative and the gradient more or less immediately, or
Time derivative.
I mean, I'm thinking in terms of this LP theory for heat equation. Like in this appendix in the book by Pierre Lyon on fluid mechanics.
Yeah.
That if you have whatever in the right hand side, then the time derivative and the Haitian are more or less in the same space. My question is if you have a similar result here.
I don't know actually.
Maximum.
Yeah.
Yes, yes, the maximum thing. Yes.
Yeah.
Thank you.
Yeah.
Questions? Short, naive question. And can you construct solutions which satisfies your Serine-Ładyżańska condition? Is it known that they exist?
Yeah. We can okay. So if we are still,
but can you construct, for example, small perturbation of equilibrium?
Yeah. We can do. Right now we can look for the low coexistence, but we don't know how to look for the global existence near to vacuum, near to zero. Yeah, because come from the Boltzmann and Landau equation. It is the chain rate. If we put the condition satisfy, we have this coefficient, it is chiefly positive, then we can go back to using the classical argument to do, because this one it is like a fractional Kolmogorov equation. But that equation, that case, they only consider near to Gaussian, near to exponential E something. So, and in that case, if we consider Boltzmann and Landau equation on the whole domain, that is my opinion, that is not the physical problem, because we don't have the finite total mass. Because we consider on in S on the whole domain, then the function only depend on V. Of course, that one is the infinity when we take the integral in S, and then we get the infinity. But in that case, but if we consider the problem on the body domain, and that is the physical, that is my opinion. Yeah.
Okay.
Yeah.
Thank you very much. Let us thank the speaker once again. Now, announcement.
Yes, since the sun came up, we decided to take the picture now.
Yeah.
Can we, before the coffee break, can we go outside to take the picture of the group? So
Yes.
Laura is here, so.
Yeah. Thank you. So,
Great.
functional.
Not prisoner.
Typically social less than one.
As a kind of universal.
I mean, it is complicated.
You don't need
Attracted by this even blower or kind of X power minus 2 or minus 1. So for P bigger than 2, I'm talking just about P bigger than 2, otherwise it's so okay, that's good.
鈴木さんの娘が好きなの。ありがとう、わかんないな。みんな持ってくる。
レシートシェアしませんけど、ホテルのレシートって我々がしたことあるんですけど、
こちらは、10%宿泊費がないから、それなのやっていいから、だから、分からなくていいじゃない。
なんかそれよくわかんなくて、持ってたら持ってった方がいいんですか？
持ってった方がいいかもしれないけど、でも俺、とりあえず何もせずに PDF ファイルだけ今送ったけど、反応ないから、まあ、一応明日からさっき持ってる。
あれ、だってリターンチケット。
いいチケットでいい。
あのチケットいいんだ。
それ、旅費全部出してもらうと、オリジナルボーディングパス。
言ってましたよね。時間、滞在時間の確認だけです。
そうそうそう。そうそう。
変なし、予約書でもいいぐらいのもんです。予約やつ変えられちゃうからいけない。
はい。
で、まあ、ありえなくはないけど、猫が落としたんだけど、めっちゃ悪くして、すげえ締めてるみたいな。
で、はい、そうだ。
そうなんだけど、書いてあるのに、なんでダメだって言うんじゃないかな。あ、そっか。朝まで楽しみに。
話題を。Probabilmente io suggesto pensare di fare capo dottorato fatto un video adesso ma devo fare anche la fisica. C'è ancora un altro giorno. Primo anno verso il cielo. Secondo anno devo fare tutti questi anni devo fare una presentazione di quello che ho fatto breve, però sul pochi, no? E il terzo anno devo fare una presentazione di esame al collegio. Quindi poi sì, l'atto di versione non l'ha proposto. Non pretendo, bene. Lo sento no. Di queste c'è anche il CD, diciamo, e e qui diciamo che è rimasto diciamo, acceso per tutta la legge senza La mia mutande anche lasciata, tenga pure, voglio dire, però di quel punto no, ecco. Che spasso, diciamo. Un po' turbato della segretaria del centro Clio. Devo dire di aver capito. C'è proprio il segnale che non hai visto la lingua è proprio, vuol dire, un segnale molto preoccupante, capito? Se cominciano a adottarti quelle, vuol dire che è un disastro. Ecco. Ci ho mandato, se uno di questo che faccio, questa settimana la prossima attenzione sulla ho mandato, dato in un discorso, mi sono dimenticato di dire che la lascia. E questo a un certo punto mi chiama, cioè si aggirava e non trovavo gli studenti, capito? Cosa c'entra? Cosa c'entra? No, guarda, comunque è una roba. Bellissimo, bellissimo, devo dire, quando l'hanno aperta c'è però c'è ancora adesso c'è abbastanza vecchio. Quando fa fare in grado che quando vanno, adesso sono queste cose di persone, anche sta sviluppazione so che devi fare un altro lì c'è il fare fantastico era gigante la giornata persona dice che su cui facevano sì, sì, sì. Secondo le sue azioni,
そうか。誰が言うわけじゃない。だから、多分その辺全部、あれだな、
poi il fatto che sì, secondo me quello sono spiegare forse sì il vento così cioè tu pensi
どうしたら崩壊。なんか投げてやったのね。
あの話だってね、この前してたんだけどね、veramente運動してやれる、運動して健康になるから、perché in Europa il giorno dopo preso sempre.
そこまでは言ってないから。なんかトリビアルじゃないですか。食べなきゃやってる。運動すれば結構。
Il fatto che lui dica che venga
証明してトリビアルです。俺は運動もしてるし、食べ物を減らしてるから今すげえのが。絶対お前の手入れはそれに
食べなきゃやってるだろ。食べなきゃ健康にやってる。食べなきゃやってる。
これはまあ。
飲んでるかもしれない。
じゃあ、今日2人でディナー行って何も食べないで帰ってきた。
何ってだ俺とお前
私。
あ、ごめん。無理。
あなたと私。You are
松さん、帰って寝なさい。見えないものが見える。すごいこと。
Posso dire questo? Sanno abbastanza vicino ci vuole Ci pare di vedere dove stai.
Some quadratic growth. So, what is some quadratic? The point is that you can do it either way, you don't mind passare, you don't mind about passare, yeah, so if you like there's every rotation then And then, conclusion the value that the point in either direction. What powers work when. And Einstein in particular, for video, for fusion, if you put the fusion and everything, you don't have anything. But the good point that whether there are steady states, goes almost to delta, or you can't take the time. No, it's so the chemistry of animals, right? If one of them changes the relation,
I'm taking the original.
but then you can drop the time derivative of the box, which is what everybody calls balancing. They call it you want parabolic when you say that chemical attraction is much slower than the other one. That's all very much. But the very most important is the model diffusion, simulation, and the conclusion that you have very important is propagation. Because if they were both diffusing, then it's really madness, but these guys can generate this next equation. And so the process is variating between the annihilation domination range, the diffusion domination range, and the fair competition. The fair competition is a relation between the exponent of fractional and fractional ranges and
Yeah, no, not the microphone.
Yeah.
So that's.
Yes, yes.
Sorry, no, I'm joking.
50 minutes later.
Thank you very much. Well, let us thank you again. And the next talk is by Edgar Pimentel, who will speak about the fully degenerate nonlinear diffusion from PD to interfaces. Please, audience is yours.
Okay, thank you. Thank you very much for the introduction. And I mean, thank you all for being here at 5:15. I truly appreciate the invitation from this organizing committee. I like very much being in Madrid. And when I got the invitation, I was first very happy. And then I was very surprised. I mean, how come this fine group of people stumble upon my name and think of me to this type of thing? So I was very happy and I'm truly grateful. So thank you. Thank you for that. Okay, so today we're talking about degenerate fully nonlinear diffusions. I'm just reading the title, From PDEs to Interfaces. And the outline is more or less like this. I'm interested in 3 questions involving degenerate diffusions. And the first one is about the free PDE, the pure PDE. So we have a PDE and that degenerates as a power of the gradient. And we are interested in examining this equation mostly from the viewpoint of regularity theory, right? And then once we know 2 or 3 things about this PDE, we'll try to embed it in the context of free boundary problems in something that we might have called free transmission problems, right? Because it must have a name, right? So this is the name we attach it to this class of things. And then first we examine the existence of solutions, and then we talk a bit about the optimal regularity for the solutions of this beasts. Okay, so let me share with you the problem. So we start with this equation here. We have f is a fully nonlinear elliptic operator depending only on the Hessian, and this object is pre-multiplied by this function sigma of the real line. I mean, let's say the positive real line, non-negative part of the real line, and here we have a right-hand side. There's a source term, right? And for me, f is a lambda elliptic operator, which means nothing but the fact that these 2 inequalities are mutually satisfied every time m and n are symmetric matrices and n is non-negative in the sense of matrices, right? So what I'm saying is that when I am on top of matrix M and I move in the non-negative direction, n, the operator satisfies these 2 inequalities, and those are weighted by lambda and capital lambda. This operator, this inequality could be this guy here minus this one. We will have Laplace operator. Here we have minus Laplace operator, right? It's just a matter of what you prefer. The source term is essentially bounded function that becomes bounded because it is continuous. And the only reason why we ask the function f to be continuous is because we want to operate within the framework of C viscosity solutions, right? We want to work with viscosity solutions, but here testing against C2 functions. So we need to be in the context of C viscosity solutions, and then this guy has to be continuous. And then there is this ingredient, sigma, and this ingredient, sigma, has to satisfy a magical assumption. And the magical assumption is that sigma minus 1, which means its inverse, has to be Dini continuous, right? You don't ask me why. I mean, if I assume that it's Dini continuous, things work, I'm happy, I come here, I give a talk, and it works. I mean, I don't know why, but this is an important ingredient. Good. So what does it mean to be Dini continuous? To be Dini continuous means that this integral here is finite for some tau that is strictly positive. I mean, the problem here is close to the origin, so this can be your favorite small number. And there is one thing that is funny about Dini continuity that has to do with the connection of Dini continuity and Hilbert continuity, right? In the sense that you can be Dini continuous, but you can fail alpha Hilbert continuity for every alpha. And this is an example of a function that does this thing, right? Good. So what if we set sigma of t to be t to some power p? Then what you have is this equation here, the gradient raised to some power p, and this can be 0, this can be 1, this can be f. I mean, this is just for the sake of talking about this class of problems for a bit. So what happens here? What is the motivation to study this class of problems? So the first thing is, well, you can think of this as it's kind of far-fetched, but you can think of this as some sort of non-variational P Laplace operator, right? What you have, if you expand the divergence over the gradient, P minus 2 times the gradient, you have something involving the infinity Laplace, and then you have a power of the gradient times the Laplace operator. So you have something like this, right? And there is a paper from 2005, if I'm not mistaken, by Christina Brendel and Professor Vasquez in Indiana University Math Journal, also if I'm not mistaken, and I'm sorry if I am, where there is a porous median equation in the presence of the gradient square, right? So it's again one of those diffusion problems, degenerate diffusion problems, when you have something that is strictly non-variational in the problem. So this type of non-variational counterpart may make sense somehow, right? Well, if you have series causal solutions to this problem, they are of class C1 alpha, and here alpha is bounded from above by 1 over p minus 1, and also by this alpha 0. This is the exponent that pops up in the Krylov-Safanov regularity theory available for the equation FD2U equals 0, right? And depends only on dimension and on the ellipticity constants. And it's been studied by Isabelle Birindelli, Françoise de Minguel, in a series of papers. I mean, the regularity appeared in 2014, but in a series of papers, they've been studying a lot of important problems concerning this equation. Cyril Imbert and Luis Silvestre, Damião Araújo, Gleidson Ricardo, and Eduardo Teixeira. We did a few things about these problems as well. And more recently, Cristiana Di Filippis and Sumia Basurji, Sung Sik Byung, Kiam Lee and Sishan Lee also studied this type of problems, right? Well, but you see, there is another class of things that is very interesting. There's the equations that hold only where the gradient's large, right? You see, you have a PDE, you don't know where it holds. You have a domain, potentially it holds everywhere, but you say, well, it holds only where the gradient is large. Let's say the modulus of the gradient, the norm is above half. So what happens is you have this type of operator here. The gamma plays the role of the half, right? And you have a PDE, and here you have a drift term if the gradient's above something, and you have no information otherwise. You see, the thing is that solutions to this problem are actually of class C alpha, and it was first established in the context of series causal solutions, again by Cyril Imbert and Luis Silvestre, and more recently in the context of merely measurable ingredients by Connor Mooney in the context of LP viscosity solutions in 2015. So you see the problems that this—
I don't understand, please. I don't understand why you say F equals infinity. What do you do with infinity?
I mean, I could have written, I don't know what happens. And since I've never been to infinity, this is just a symbol I wrote. I mean, I could put anything else.
And in that part of the domain, what do you do?
In this part of the domain here, where this guy is bounded from above by gamma, we have no information. And the interesting thing is that we a priori don't know where this is, where this subregion is located, right? Yes. And the funny stuff is that it covers the case of Dini continuous degeneracy law. So if what we manage to prove is C alpha, this is already known. So the catch for us here is that we have to prove something that is strictly above C alpha threshold, otherwise it's already known, right? And that's something that we managed to do with a couple of friends. And what happens is, if we have a series causal solution to this problem and the operators, the ingredient, satisfy what I just told you about, then solutions are locally of class C1 in the domain. And for every compactly contained subset, you can find a modulus of continuity such that this estimate here is available, right? These things here are associated with the scaling argument that somehow we have to use to approach this thing. I'll talk about it. I'll talk about it a bit later. And then we have here this modulus of continuity. What I mean by local here is that the modulus of continuity depends on everything that has to depend, but also on the diameter of omega prime and the distance of omega prime to the boundary of the original domain. It's not that we have a constant that depends on those structures, but we have the modulus of continuity. We don't know how this guy behaves explicitly. We know what it depends on, right? And this is something we did with a former PhD student, Pedra Andrade. She's now in Lisbon, and two of those friends we like very much, Daniel Pellegrino and Eduardo Teixeira. Daniel is in Brazil, and Eduardo is in Florida. They're very nice. These are very nice fellows, and Pedra is a very talented former student, now a colleague. So how do we prove this type of results? I mean, the way I know how to prove these things is through this thing called this toolbox called approximation methods, right? And what I mean by approximation methods is this beautiful idea due to Luis Caffarelli in a paper 1989 in the Annals of Mathematics, where what happens is, well, you have an equation you know nothing about, you have an equation you know a lot of things about, and then you try to connect them by some sort of geometric structure, and you import information from things you know to things you don't know, and then you write a paper, you have a theory, right? So what happens here is, what we did is to use a scaling argument to relate the equation we have, the sigma f d2u equals to f, to this homogeneous equation here, right? And then the idea is to import regularity from this object to the one we have. So one ingredient that is very important is compactness of solutions, and we must have compactness for the problem we are examining, and it comes from Ishii, Jensen, lemma in the context of viscosity solutions. And we also come up with a sequence of approximating hyperplanes. We have to subtract hyperplanes and then control the growth of the solution minus the gradient in some inappropriate balls or in balls of appropriate radii. And then we have convergence analysis and produce a modulus of continuity. What is the thing? What is the key ingredient here? The ingredient is that we need to work at the level of some degeneracy laws, the sigma kappa, sigma k. This thing is something that we have to come up with then the approximation strategy as since the arguments are more or less sequential, and we have to use sequences of things like those, right? What is the catch? The catch is that the sequence sigma k may itself be degenerate. What it means, it can go to zero very fast. It can go to zero very fast, and then you lose control on how things go to zero. If it lays down to zero, like some sort of tangential decrease tangentially, then this is a problem, and we have somehow to shore up this thing. So at first we thought, well, if we assume the original sigma of t is above some constant times t, then we are safe. But this would be an additional assumption, right? So we have to somehow kill the necessity of imposing this further assumption. And then what happened is this notion of non-collapsing degeneracy. So a set of moduli of continuity will be called non-collapsing if this thing here going to zero, sigma of n, evaluated at Zn, implies this thing. So it means that the sequence sigma n cannot go to zero tangentially, because you have this some sort of shore up for the sequence, right? And it has to happen for everything, for everyone, every sequence in the sigma set. The funniest thing is that Dini continuity of the inverse ensures the non-collapsing property for the sequence that we have to use in the context of the approximation methods. And how we prove this? Well, we have to open this beautiful book by Erwin Kreisig in functional analysis. Maybe we have to do a bit more than that, but that's the way, that's what I learned about C0 things and L and the small L things. So what happens is, what we have to show is that there's two inequalities here relating sequences in L1 and C0 hold, right? If we have this type of information here, then we can make sure that the sequence, the degeneracy sequences that goes to 0, well, they only go to 0 if Zn goes to 0, right? This is a bit technical, and I'll be more than happy to discuss this with you. Can be now, can be and it can be, I mean, after the talk or any other moment. But I think this is the key ingredient to establish this result, right? And what the result gives us indeed is that, well, if you have a series causal solution to this problem, and you happen to know that sigma has an inverse that is Dini-continuous, then you have continuous differentiable solutions. So this is the regularity locally, right? This is the regularity result that we managed to prove. But you see, now we have this thing. Now we have the regularity result for the equation, and then we may want to frame this problem in the context of free boundaries. So what happened is, or what occurred to us, was to think of this. Let's think that sigma is t to the power p, right? This very simple sigma, right? And what I say is you pick your favorite p1 and say, well, in the domain enter this set that I'll tell you now what it is. We have this degeneracy law. If we go to this different set, and I'll tell you also now what it is, then you have a different degeneracy law, right? And here, once again, this is just Control C, Control V. I'm just copying what I said before. We have these things, and we order these guys, no laws of generality. And what happens is that P1 drives the degeneracy law where the solution is positive, and P2 drives the degeneracy law where the solution is negative. So what you want to do is to say, well, where the solution is positive, I have one degeneracy law. Where the solution is negative, I have another one, right? Nice. Inside this set, of course, the previous result holds, right? And then we have C1 alpha regularity. We know explicitly who is the alpha. The same thing holds here. The question is, what happens across the free boundary, namely the topological boundary of the set where U is not 0, right? So there are two fundamental questions here. The first one is the existence of this causal solution. This is by no means trivial. And the second one is the regularity of the solutions across the free boundary, right? There is this set here. What is the key difficult? The key difficult for us is that the usual methods, and when I mean usual methods, I mean the user's guide for viscosity solution, Crandall, Ishii, Lyons. What we have there, we cannot use here the way it is, right? So we have to move a bit further in the theory to tackle those questions. So let me start by telling you what we did when it comes to the proof of existence, right? So to prove the existence of viscosity solutions, well, you'll notice the operator is discontinuous with respect to U, because U changed sign and then I jump from P1 to P2 or other way around, right? The important thing is we have no monotonicity with respect to U. I don't know what happens. I don't know if the gradient happens to be smaller than 1. I don't know if it's greater than 1. You see, I don't have properness. I don't have properness associated with this operator. So if I lack properness, then the maximum principle and comparison principles, the way I know them, are not available. So if these guys are not available, if comparison principle is not available, I don't know how to apply Perron's method. So you guys can say, well, this speaker, this guy doesn't know what he's talking about. I can do this routine either way. Wonderful, but I don't know how to do it if I don't have comparison principle, right? And we were trying to do something here. And what happens is that, well, you see, what kills the thing at the end of the day is the fact that the exponent depends on U, right? So the idea is, well, how to bypass the dependence of the exponent on U. So we start with a function V that is continuous up to the boundary of omega. and we choose a small epsilon that is fixed between 0 and 1, let's say, and then we construct this function g epsilon v, right? I mean, if v is below minus epsilon, this thing would be either 0 or 1, and if v is above epsilon, this thing would be 1, either 1 or 0. I don't remember, I have to make the computations, but I mean, what you're saying here is that this function will be either 0 or 1, depending on how you compare v with minus epsilon or epsilon, right? And then you say, well, this is 0 in the line minus. There should be some d somewhere, probably is rd or omega d, or is rd probably. And then you see what happens is you modify this guy to get something that is differentiable, and that you can make computations, honest computations with that. And then you define an exponent p v epsilon that is p1 times age plus 1 minus age times p2. So what you do is somehow you convexify the thing between p1 and p2, right? You're always between those two guys using this strategy and this convolution, right? And then what you happen to do is you come up with approximations, epsilon approximations of your equation, depending on this regularized exponent, right? The funny stuff is when you study this equation here with this boundary data, then comparison principle is available. I mean, we proved the comparison principle, so it is there. And you can manage to construct global sub and super solutions. There will be these two ingredients here. Perron's method yields the existence of a solution in between, right? And you also have compactness for the family, for this family here, right? For this thing, existence of global sub and super solutions, of course, you need conditions on the domain, right? So if you have exterior sphere condition, then you can construct barriers explicitly. If you only have cone, uniform cone exterior condition, then they exist. There's a beautiful paper by Crandall, André Schiel, and Pierre Millions, and someone else who I hope is neither here, not on YouTube. And it's a paper in the Electronic Journal of Differential Equations in the late 90s, where they discuss this strategy, how the geometry of the domain relates with the barriers, right? Good. So what we do, we use Schauder's fixed point theorem to show that you can come up with a function u epsilon that solves this thing here. You see, Schauder's fixed point theorem kills the dependence on v. And then we are lucky enough to rely on compactness for the family u epsilon and stability of viscosity solution. Stability of viscosity solution is one of these wonderful things we have in life, right? I mean, you don't know what to do in life, you resort to stability of viscosity solution, the chance it saves you. I mean, for me, it's been wonderful. And once we take the limit, as epsilon goes to 0, we manage to prove this result. So what we have is we have a domain that satisfies some sort of exterior condition. The data are what they have to be. And then there exists a viscosity solution to this problem that satisfies these equations in the viscosity sense where they have to be and agrees with G on the boundary. This agrees with G is in the sense of chapter 2 in Nevin's book. I mean, the limit of ux as x go to x0, the boundary is G of x0, right? Also, U is a viscosity solution to this equation driven by the minimum, and a viscosity super solution to this equation driven by the maximum. This C0 has to do with the L infinity norm of F. And it was done jointly with a former postdoc of mine, Gerardo Aroto, who's now a professor in Brazil. Gianni Rampasso is a former student of mine, also a professor in Brazil. And my friend Andre Schiel, who's in GATEC, and he's a very fine mathematician with whom I've been learning a lot. Good. So once we know the existence of solutions, the question is about the regularity, right? So once again, we have the same slide. The operator is discontinuous with respect to U. We have no monotonicity whatsoever with respect to the solutions. We lack properness. Viscosity solutions lack stability. I just told you I've been saved by stability many times before, right? And then we don't have stability. Either we start crying, I start crying, or we have to do something else. You see, it gets worse in the sense that the maximum principle is not available, or at least I don't know a reference for the maximum principle in this context. Usual approximation methods are off the table. I know 2 or 3 things in life. This is one of them. If it's not available, I cannot solve the problem, right? Good. So we have to do something else. How do we tackle this problem? If you use a continuous function that solves the free transmission problem, then it solves in the sense of viscosity solutions this inequality, right? It's the minimum of a bunch of things controlled from above by a constant. Notice that now it doesn't happen only in omega minus, omega whatever, it happens in the entire domain, right? And a similar inequality driven by the maximum is bounded from below by minus C0 also in the entire domain. So the important part here is that you have PDEs in subregions of the domain you don't know a priori, but they translate into inequalities that hold in the entire domain. And those inequalities somehow relate with the extremal operators and give you information, right? So what happens is the matrix inequality in the maximum principle, this is Ishii-Jensen. This is Ishii-Jensen inequality. I think this is chapter 3 in the user's guide in the bulletin 92. And we also have compactness through C-beta estimates. Stability of solutions is available, and we'll try to import information from f equals to 0 to those inequalities, right? And this is indeed possible, and the theorem we managed to prove is this one. Here we have the omega is B1. It's been always B1, right? But this is the slide I tell you, this is B1. And what happens is we choose our favorite alpha between 0 and the Krylov-Safonov exponent, constrained by 1/1 plus the maximum of these exponents. Of course, if we stick to what we said before, 0 strictly below P1, strictly below P2, this would be just 1/1 plus P2, right? Then solutions are C1 alpha locally in the unit ball, and for every tau that we have, the C1 alpha norm in B tau is bounded from above by this quantity here. This is how the scaling affects the source term, right? Where this constant depends on everything, it has to depend, and also on tau, right? And this result was also proved with Gerardo Arotto, Gianni Rampasso, and Andrei Schfiel. And this was what's quite an adventure to think about this problem with these friends. So one neat consequence of this theorem is that if we have a degeneracy law that is given by this exponent here, then a solution to this problem also satisfies these inequalities, and the theorem extends to something like that, right? So what is the strategy of the proof? We scale the equation to assume this is sufficiently small. I mean, this is a standard kind of trick, and we approximate the original inequalities by homogeneous inequalities, right? Because C0 is small, then we can say, well, these guys are really close to something there is 0, right? And then there is a cancellation that appears here in the viscosity sense. The first time I saw this cancellation strategy is in this paper by Cyril and Louis Silvestre in the Advances Mathematics. I think it's a beautiful idea in the sense that if you have the gradient raised to some power multiplying the operator, and this is 0, solutions to this will be solutions to the equation f equals to 0, as if you can cancel the gradient, right? And this context means that if we have minimum smaller than or equal to 0, then it solves f smaller than or equal to 0, and the corresponding thing also for the maximum. And then we resort to these standard approximation methods, and we complete the proof. Good. So what's been done since we wrote those papers? So there is one interesting thing in the context of non-homogeneous degeneracies, and it was done by Cristiana De Filippis and appeared last year in Interfaces and Free Boundaries. There was also the case of state-dependent exponents. It was done by a student of ours in Coimbra. There is David Jesus. David Jesus just completed his PhD. He's now in Bologna as a postdoc with Fausto Ferrari and his group. And it's also something that is related to what we did. And one thing we've been just finishing recently has to do with boundary regularity for sigma Dini continuous problems, and that's something we've been doing with this friend of ours and a former student, David Stonitsky, former master student. David did his PhD in Homo sapiens, is now in Technion in Haifa, and I mean it's been pure fun to talk about these things with David. And well, those are things we know how to do, but then there are things we don't know and we would love to learn about. The first thing is the regularity of the free boundary associated with free transmission problems. I mean, I have no clue whatsoever on how to start. And maybe it's easy, maybe it's not, right? So this would be something we would be very much interested. And the other thing is, if you notice, I kept mentioning that there's a C viscosity solution, C viscosity solution, C viscosity solutions. There is no LP viscosity theory available for this class of degenerate fully nonlinear diffusions. So one thing that for me would be very interesting is to pursue, or I mean, the word here has to be developed, because this is not available, and it should be something interesting. Instead of testing against C2 function, test against W2D functions would be a dream. I'm not sure this is something we know how to do. There's this last thing, there's the Harnack approach. I mean, the Harnack approach is something like that. I mean, you touch the graph of the function from below, let's say with the modulus of continuity, and you want to understand conditions on the function that allow you to drop, to flip this modulus of continuity, right? So, I mean, if a function is in the George class, then this type of things will happen if the function has a weak Harnack inequality, satisfies a weak Harnack inequality, and some sort of generalized maximum principle. This would happen. My question is, what type of information we would get in the context of fully nonlinear free boundary problems through this approach here, right? So these are things we would like to learn about, and I think we managed, right? Wonderful. So with that, I thank you very much for your attention.
Much questions, comments?
Yes, please.
So can you, thank you very much for your talk. Can you attend your result to the equation like Hessian or moment-based equation when you replace your operator F by something like moment-based for nonlinear?
You mean here?
Yeah.
I don't understand the question.
Mode compact.
Oh. I don't think so.
Because that's the equation.
I don't think so.
For the geometry or...
Yeah, I don't know. And that's a beautiful question. It's a beautiful problem. I have no, yeah, I don't know that. Yes.
Yeah, so, and I have another question. So, because you look, your solution is C1 alpha. And
yes.
If I check the 1 point, satisfy the relative yield far from 0, and then because your solution is C1 alpha, and then you can look around that point, you have the relativity positive, and then in that neighborhood, your solution will be smooth. Yeah, right?
Yes. Yeah. I think this is true. I think this is true. Yeah.
because after that you can remove the term gradient of U power 2.
Yeah, then I wouldn't say smooth. I mean, I would go. I mean, if you have convexity of F, you would go. I mean, unless you mean by smooth you mean C2. I wouldn't go beyond C2 alpha. I mean, the Evans-Krylov thing, right? Because even if you are uniformly elliptic, you have F d2U equals F, right? You need some regularity in the right-hand side, and you need convexity, and this type of thing is very delicate. But you can go classical. Definitely, you can go classical. Yes, you're right. Yes.
So, and I have another question. So you define viscosity solution, but using some special approximation. So can you group, if I give you another approximation, can you group the units, the limit?
Yeah, I mean, for you to have unique, you can prove uniqueness for every epsilon, right? Because at that level you have comparison.
But we'll know how the limit is used for any.
We don't have uniqueness at the limit. At least through this approach, we don't.
Yeah.
Yes. Interesting. Thank you for the question.
Questions? Do you know that Andrzej Święch is Polish?
I know we used to talk about Krzysztof Zanussi and Polish movies.
Okay, good.
I mean, that's how we started.
He's ambassador of Polish countries.
Yes.
You have a question?
Yes, I was wondering about your compactness estimate. You had some folder continuity bounds.
Yes.
So how do you get to these bounds?
This is beautiful. I mean, there is the Jensen-Ishii lemma that somehow you work at the level of doubling variables, right? And then you have you have an inequality that if it's satisfied, you have either Lipschitz or Civita, right? So or Hilbert. You assume it doesn't. You assume it fails, right? And then this Ishii-Jensen lemma gives you a beautiful contradiction by making some choices in the constants, and those choices that you make gives you the norm. So yeah, it's in this Ishii-Jensen lemma in this.
How does it become independent of your parameters? This other.
Yeah, because it depends on ellipticity. Strictly in the ellipticity, and depends on those estimates are local, right? So you fix the thing, you fix the subdomain, and you work inside of that, right? And once the ellipticity is fixed, then all the other, I mean, the norm of f, the small f, is also fixed. Then you have all the constants that will somehow get together to yield contradictions. Yes. So you're independent of epsilon. Yes.
You have interior compactness.
Yes.
Yeah. Okay.
Yeah.
Let's see. Let us thank the speaker once more.
Thank you. Thank you very much.
Thank you to all speakers today. Today is closed. Enjoy the evening. We meet at dinner.
We meet at dinner, yes.
See you. 9. At 9.
At 9. The session.
Estuvo genial, it was incredible. We have fixed this kind of problem with the discontinuity of the operator in one of our last papers, and more than the problem I don't know because what you say very good at the beginning, this is a applied. I mean, the other operators have been applied and somehow have been one